In this session, we will discuss about the three-dimensional state of stress. In the first session, I have discussed about the various loads acting on the engineering materials and how we can resolve the system, or how we can find out the internal resistive force, and the concept of stress was explained. So in that particular session, I have told you about considering a section so that we can define a stress. Similarly, if we take a cuboidal element or a three-dimensional element from a loaded material, then how the stress is going to look like? That is the point of discussion here. So when you take a material, when you take a cuboidal element, we are idealizing the analysis to a cuboidal element which is taken out from a loaded member. So you can see that there are different type of stresses acting on the system. But there are some speciality to these stresses which are acting on the surface of the cuboidal element. What are the specialities? You can see only mainly two type of stresses. One is the normal stresses which are acting perpendicular to the surface. The sigma x, sigma y and sigma z. Those are the normal stresses, because we are interested only to find out the normal stresses and as well as the shear stresses. Here you can see another type of stress which is nothing but the shear stress, tau xy, tau yz, like that you can see here. So this kind of representation is known as the general state of stress. We are expressing all the types of stress in a cuboidal element. It doesn't mean that a three-dimensional element or a cuboidal element that is taken out from a material, loaded material, should have all these components. We cannot compel to have something like this. It is purely based upon the loading. Suppose if you don't have a loading in the z direction, you will not have component in this particular plane. You will not have a component in the dy dz plane. You will not have. That is how you have to understand it. So it's purely based upon the loading. Now let us move into a biaxial state and a triaxial state. Triaxial means three axes. Stresses are available in the three perpendicular axes. So this is an example for triaxial stress. When you compare these two figures, you can see that the shear stresses are absent in the system. So that is also a possible scenario. Doesn't mean that always the shear stress should generate. No, there is no condition like that. So in this case, there is only normal stresses. But if you look at this first figure, you can see that the stresses are only in two mutually perpendicular direction. First direction 1 and direction 2. So this direction can also be called as x direction, and this direction can be called as y direction. Okay. So the z direction, the loading is completely out. There is no loading in the z direction. That means we need to consider only the x and y axis. So since two axes are involved in this analysis, it is called as biaxial state of stress. So in this session, we will be discussing in detail about the three-dimensional state, and followed by this session, we will be discussing about the two-dimensional state, how the assumptions are made, how we are idealizing the system into a two-dimensional state, all those things. So this is called as a general state of system, and the stresses which are acting perpendicular to the surfaces are called as the normal stress. Now we have to understand the normal stress equilibrium. We have already told that everything that we are going to discuss under mechanics of solids is going to be within elastic limit, and also it should be in equilibrium. So what is the condition of equilibrium for a stress, especially for a normal stress? So if you take only one direction, let it be a uniaxially loaded member. Uniaxially loaded, you can consider only one direction. So simple equation for equilibrium is what? F of y equal sum of the forces in the y direction should be equal to 0. So sigma is nothing but stress. They are not forces. So in order to obtain the force acting on this particular plane, we have to multiply this stress with the area. So sigma into delta S is going to act in the upward direction, and sigma dash into y is going to act in the downward direction, like this. So sigma dash into delta A is in opposite direction compared to that of sigma into delta A. So when we equate this, sigma into delta A minus sigma dash into delta A will be equal to 0. Delta A will get cancelled out. Delta A will get cancelled out, and the term that is, or the final conclusion that we can arrive is what? Sigma is equal to sigma dash. That is the final conclusion that we can arrive at. This one. So in order to have a equilibrium in the normal stress direction, the value should be equal and it should be opposite. That is the reason why we are representing a sigma 1 opposite to that of the sigma 1 in the opposite phase. So that is the reason why we are specifying it. Even though in this general state of stress we haven't shown the opposite side, but you have to understand that a similar state of stress but with the opposite direction exists on the opposite face of this cuboidal element. Now moving into the shear stress equilibrium, we have to understand the nomenclature, how the stresses are read in a system. That is very important. So usually along with the shear stress, even normal stresses are also having two letters, but still generally it is not used in normal stresses. But in shear stresses, they are always associated with two suffixes. So what are the meaning of these suffixes? So the first letter indicates the direction of the normal on the plane. That means if you consider this particular plane, then the normal on this particular plane is in the x direction. Okay, so all the shear stresses acting on this particular plane should have the first suffix as x. So you can see here x. If you consider the top surface, the normal is directed towards the y-axis. So all the shear stresses acting on this particular plane will have the first letter on the suffix as y. Similarly in the z direction. So this is how the first letter is read. What about the second letter? Second letter clearly shows you the direction in which this particular shear stress act. If you look at this particular plane, we can see that tau x and this shear is acting in the z direction. This is the z direction, it is acting in the z direction. Similarly, this shear it is acting on a plane which has a normal in the x direction and it is acting in the y direction. So it is named as tau xy. This is how you have to read or understand the stresses. Now we have to discuss about the equilibrium condition for a shear stress. To make it clear, or for a better understanding, let us limit our discussion to two-dimensional state. So you consider a system which is in a two-dimensional state. We are not considering the normal stress, a pure shear condition we have taken, and we can see this particular plane has a shear stress, this has a shear stress, this has another one, this has another one. Now we have to understand what should be the value of the shear stress, or what should be the condition to provide a equilibrium in this case. So for that case, let us take the tau zy condition. This tau zy normally is acting in the z direction and stress is directed towards the y. So we have to submit force in the y direction. Y is this direction. So it should be equal to 0 according to the equilibrium condition. So now these are stresses. We have to find out the forces. In order to find out the forces, we have to multiply the stress with the area. So this tau zy is acting on an area on the top surface whose area is nothing but delta y into delta x, right? So that is given over here. So the first term gives you, the first term is nothing but the stress value. The second term is nothing but the area. It is clearly mentioned here, area. So multiplying these together will gives you the force value. It's very simple. So if you consider the y direction, you have got two shear stresses, one on the top surface and second one on the bottom surface, and this bottom surface shear is mentioned as I think it is not visible, it is mentioned as tau dash zy. This is how it is mentioned. So the value of force is going to be tau dash zy into delta x into delta y. Again if you cancel out these two terms, what is the value you are going to get? You are going to get it as tau zy should be equal to tau dash zy. These two values should be same in order to have an equilibrium. Similarly, if you and again if you take the moment of these forces, that means moment means tau zy is going to create a moment about the x-axis, right? So that's the reason why we are taking the moment about the x-axis. So you can see if a force is acted over here, the entire rotation is going to happen in a clockwise manner like this. So it's a moment or in the opposite direction. Okay, so this moment is happening with respect to the x-axis. That is the reason why we are considering the moment about the x-axis. Now, so if you take the moment about the x-axis, let us see how it is going to look like. So first we have to find out the force multiplied with the perpendicular distance. So we know how to find out the forces using the above relation. So tau zy into delta x into delta y gives you the force into delta z, because the perpendicular distance is delta z. You can see the height from the x-axis. So this value is going to give the moment, and the sign convention negative means clockwise is considered as positive here. So that is up to us whether to take the clockwise as positive or anti-clockwise as positive. So that is completely depending upon our way of doing it. You are free to take the opposite way also, you will get the same answer. So this term gives you this moment about the force tau zy, and if you consider the second force tau dash zy, this one tau dash yz, this one, this plane. What is the value? Sorry, tau dash yz is tau yz, this one. These two are the forces which is going to create a moment on the x-axis. So the value is going to be tau yz into what is the area, delta x into delta z, that is given over here, and finally the perpendicular distance is nothing but delta y, force into perpendicular distance delta y. So when we cancel out the similar terms, these two terms will get cancelled out, and only thing that is left with is tau zy should be equal to tau yz. So this is a very important condition that you have to study in order to have a proper shear stress equilibrium. The shear stresses acting on the opposite planes should be equal. That is derived here, tau zy equal to tau dash zy, and also the tau zy should be equal to tau yz. That means tau zy and tau yz, these two terms, these two shear stresses acting on the successive perpendicular planes should be same. So if this is same, this has to be same, these two has to be same. So that means this and this will be same. That means all these shear stresses acting on this particular system has to be the same, tau. Since it is a two-dimensional case, we are simply given as tau. Otherwise it should be tau xy is equal to tau yx, tau yz is equal to tau zy, tau xz equal to tau yz. Everything is one and the same. So this finding or the concluding that this tau xy is equal to tau yz is nothing but the principle of complementary shear stress. So if without satisfying this, there will not be kind of equilibrium either in the force side or in the moment side. So that is very important. So this is how we have arrived at the shear stress equilibrium. This is a very important concept when you learn the three-dimensional state of stress. This is called as the principle of complementary shear stress. So in order, if you consider the other direction, here you have taken the which one, tau zy and tau zy and tau yz, right? You can take tau xy and tau yx, you can take tau xz and tau zx. All these can be taken into account, so you can find out the corresponding complementary shear stress relation between the planes. So combining all these things together, we will be obtaining something like this, a three-dimensional state of stress. Here this tau yx and tau xy should be same, tau yz and tau zy should be same, tau zx and tau yz should be same. Now If we take the three-dimensional case, we have already discussed that this cuboidal element is being taken out from a loaded member. This is something which is lying inside the body. So if you represent this entire system of state of stress into a single quantity, it will be of a matrix form. So the diagonal elements will be the normal ones, sigma x, sigma y, sigma z. And if you consider, let us say, if you take this as the x, and if you consider this term corresponding to this as y, and if you consider this column corresponds to z, then it is easy for you to understand. Similarly, even if you plot, let us say this is for the x and this is for the y, and if this is for the z, then it is easy for you to identify the things. So if you take the crossing of these two, that means if you draw a line from x to bottom and from here to here, the coinciding point is xx, right? So this term is represented as sigma xx. So that is also another way of representing the normal stress. There will not be two different variables, it will be single variable, sigma xx, sigma yy, and sigma zz. And when you take these two cases, the x and y, these two terms, or these terms other than the diagonal elements, all the other terms are shear stresses, and this is going to be tau yx, and this is going to be tau zx. Similarly, if you look into this particular matrix, we can find out all these values easily. Okay, that is very simple. Now, if you look here, we can say that sigma xy and sigma yz are one and the same, sigma xz and sigma zx are one and the same, sigma yz and sigma zy are one and the same. That means this is a symmetric matrix. This is called as a stress matrix. Stress matrix are always symmetric. That is a very important point. Stress matrix has to be symmetric. That is a very, very important point that you should note down when you consider a stress matrix. Now, this way of representing it is called as a tensor. Now, how will you understand a tensor? It's very simple. If you take a scalar quantity, it requires only the magnitude to represent it, or to get the complete meaning of a system, a scalar system, we require only magnitude, 5 kilo, 10 kilo. It's understood what is the meaning of that. But if you take a vector, it requires two quantities. One is the magnitude and second one is the direction. That means if somebody says velocity of 5 meter per second, the idea is not conveyed properly. In order to get a clear-cut idea, he should say in which direction this particular velocity is going to or is acting. So a direction is very much required along with the magnitude to understand a vector quantity in the proper sense. But stress is not even a vector, because even if you say that a stress in a particular direction, the idea is not conveyed. Why? Because I told you that in the first session, stress is an internal phenomenon. It is acting on a plane. That means there are infinite number of planes that can be considered within a material. So all these planes will be having different type state of stresses. This particular state of stress is in a particular plane. So if you change the plane, another set of state of stress will be obtained. That means it is purely depending upon the plane direction. That means you require a location to define the state of a stress. So the stress at a point is valid only at a particular location. It requires a magnitude, it requires a direction, as well as it requires a location. So a quantity which requires all these three are considered as a tensor. So stress is nothing but a tensor. It's a second order tensor, since it is a quantity associated with two directions, two subscripts, directions of the surface normal and direction of stress. So it's a second order tensor. So you have to understand the concept of state of stress, the way it is being represented, the property of the stress matrix, which is nothing but symmetric, the principle of complementary shear stress, all the equilibrium conditions, all these things should be considered when you understand or when you analyze a three-dimensional state of system. This is the simplest way of explaining the three-dimensional state of system. So in the coming session we will discuss about transformations of the stresses. The two-dimensional state of stress we will be discussing in detail. So three-dimensional stresses are not general, we are not going to study in detail, but still we will discuss about the dimensional state of stress in the coming classes, but our entire focus will be on the biaxial state of stress. So in the next session I will discuss about the stress transformation. How can you find out the stresses in different planes? So what are the equation, the derivation, and how you should analyze all these things will be discussed in the coming class. So kindly go through this and have a nice day.